All right, so the lab session today is going to focus on relating the concept that we have introduced earlier in the lecture, but this time we'll do it in LogicSim. Okay, so you kind of have to map, the stuff, the concepts that we have just introduced to, what we're going to do in LogicSim. So I'm going to start with LogicSim, and you can follow along if you want. It's not required, but I think your time will be better spent just by looking at what I'm doing and thinking about it, and then ask questions when you don't understand. Okay, how does this piece connect to that piece? There we go. All right. Yep. Go ahead.
Is it necessary to convert all the gates into NAND gates and then operate from there, or can we just use the gates provided?
You can use the gates, but I can go ahead and kind of explain everything, like how I make up these individual components. Okay. All right. So the first thing I'm going to do is I will start a new circuit just to deal with the carry. Okay. And this is going to be an easy circuit. Okay. So the carry circuit is going to have how many inputs? If you look at the function, the C function, how many parameters are there to the C function? 2 parameters, because you're adding 2 digits, and then the answer is, do we have a carry of 1 or do we have a carry of 0? Okay, so that's good. So we know there are 2 input pins. Okay, 2 input pins, and we can label these X and Y just like, just to be consistent with the notes. So this is X, this is Y, each one is a single bit. Okay. And then we have an output, and I'll label the output as C, which is carry, or to be consistent, I'll use K, because I use the letter K in the notes. So the function that is mapping the input XY to the output K is what we need to specify here. Now, since LogicSim can only deal with binary stuff, okay, so we are now confining our addition to binary addition. So in binary addition, what is the other way to compute the carry of adding a single bit to another bit? The logical AND gate. Okay, so when you use AND in a calculation or in an equation, to do it in hardware, you go to the gates, you specify an AND gate, and then you just put it in the circuit here. We only need 2 inputs. Now remember, do not leave any input pins unconnected, because that is just really, really unsafe practice in electrical engineering. And to make it look nicer, I'm going to make it smaller, just like that. Okay, it takes up more space than it needs to, but that's fine, not a problem. So I'm going to connect these 2, and connect these 2. There we go. So now we have the function to calculate the carry of adding X as a bit to a Y, which is also a bit. Okay, pretty easy. So what we'll do is we are going to change the appearance, make it a single chip, give it a name. So we'll just call this, carry, which is C. C is the name of the function. There we go. Okay. Are there any questions for me? Huh? You just right-click and then go to Edit Circuit Appearance. Okay. Yep.
Where do you get the carry?
Huh?
I don't see carry on my screen.
Okay, so what I did before was looking at the circuit of the layout of the circuit. So to get to the appearance, you right-click on the circuit that you're working with, and then you click Edit Circuit Appearance. Then it will give you the default look, which is a chip.
Oh, okay.
Okay. So the next one I'm going to make, so we go back to project, we say Add Circuit, and this time we want to deal with the R, which is the result. So we say this is the result chip, okay, which is also kind of easy. It has got 2 input pins because once again we are adding 2 bits. So we have the first bit and the second bit, and then we have 1 single output, which is the result of adding these 2 bits. Now Here I can cheat a little bit. I can say, you know, I can use an exclusive OR gate, but since, you know, in the class notes I did not do that, I'm going to stick with my class notes and use the AND. Yeah, I'm going to use one OR gate and two AND gates to do it. Okay. So this will do exactly the same thing. We go to gates, and then we specify an AND gate. First thing to do is to change it so it has two inputs, and also make it smaller. So, and I'm going to duplicate it because we need two of these things. Okay. Now, the one thing about these AND gates, or just about any gates, is you can specify that one or both of the inputs to be negated. Now, so let me show you what I mean by that. When you look at this part here, see how it says negate top and negate bottom. So you can say yes on one of them, and you can see how the bubble, you know, appears right here. So that means whatever you feed into this pin here is going to be negated before feeding into the AND gate, which is exactly what we need. So for the second one, I'm going to negate the bottom, like so. Is that okay? Yep.
So what does this mean in terms of expression?
Let me label the input pins first, then I can refer to the input pins when I spell out what they do. So let's call this X again, and call this Y again. Okay, so when we have labeling like that, then this particular output is not X and Y, because the signal X is negated before it gets into the actual AND gate. The bubble means negation. But the signal from Y is not negated. So and this is an AND gate by itself, so it is not X and Y. And then the other one, obviously, is X and not Y. When I connect these outputs into a OR gate, then I have, you know, the exclusive OR effect. So we have an OR gate here, specify only two inputs, and make it narrow. Connect it like that, and this one like that. Here. Okay. Is someone playing my video, or I am playing my own video somewhere?
Are you hearing that now?
I'm hearing a chatter. Huh?
People talking outside.
Oh, okay. I thought I was hearing voices. No, that's actually next door. That's actually next door. Yep. All right, so this is the result, you know, circuit, which is also just exclusive OR, but since I gave you the equation that is not using exclusive OR, I'm going to use this. Is that okay? All right. So we'll go ahead and do a right-click on this circuit, you know, and say Edit Circuit Appearance. So now we're making a chip out of it, and we'll use R here, just so that we remember this is the R function. Okay, so we have the R function here. Very good. So I have just made two components on my own, and each one is really simple. One is to do the C function, one is to do the R function. Is that okay? So now we want to specify, you know, okay, but how are we going to add two numbers? That's the question. How are we adding numbers? There's several ways to look at this. Okay, so let's go to main, go back to main circuit here. We'll go ahead and do it, you know, to a certain point, and then we'll rip it apart and then do it, you know, differently. Because, you know, the first way to do it is very, very tedious, and it is definitely not going to be very effective. So we're going to do it the hard way first, okay? And so we'll specify a whole bunch of pins here. Actually, I could do something like this. So we'll call this one, you know, X0, and this one is Y0. And then the output, so this is the first column. X0, Y0 are the bits that we are adding in the rightmost column in the class representation on the whiteboard. And then the output, the eventual output of this is going to be labeled S0 because it's bit 0 of the sum. Is that okay? So now we say, okay, how do we do this? Well, this one is pretty easy, isn't it? Because all of this really just needs to apply the R function once, and whatever the R function is given us is going to be the result. So just connect it all the way here. We're done. Is that okay? Now you can test the design anytime you want to. So you can say, okay, is 1 plus 0 1? Yes. 1 plus 1 is 0? Yes. Okay, because this one does not calculate the carry, it only calculates the result. What about 0 plus 1? Is a 1? That's good. So we have checked every single possible case. The circuit is working up to this point. So now we want to look at the circuit and go like, okay, let's add another column. So let's go ahead and add bit 1 into this whole thing. Let me see if I can duplicate 2 pins at the same time. So now we have duplicated the 2 pins, and it's good to change the names. So this becomes X1, or the second least significant bit of X, and this is going to be Y1, which is the second least significant bit of Y. Okay. Does anyone remember how to calculate S1? Okay, I'm going to put S1 over here and label it accordingly. How do we calculate S1? Oh, it's not so straightforward anymore, isn't it? Okay, because we need several things. First of all, we need to use the result function to calculate an intermediate result. Okay, so we'll put an R here and give it all the necessary input. But this output here has a particular name in the notes, in the notation in the notes. Does anyone remember which letter I use for this particular wire? Q. Very good. Okay, good job. So to label a particular wire, there are several ways to do it. You can go to wiring, and you can add a tunnel. Basically that's a way to label a particular thing. Well, one of the things you can do with a tunnel is for labeling purposes. So we can label this one and say this is Q1. Okay. This is not required. It doesn't do anything in this particular circuit other than as a documentation, as a tag. But I find it to be particularly useful because we have that name in the notes. So we want to kind of, I will try my best to map the design of the circuit to the notes that we have just used in class. Okay. So if this is not enough by itself to become the sum, what else am I, what am I missing here? We're missing, okay, when you add X0 and Y0, other than the result, what is the other part that we might be interested in? The carry, exactly. So the carry of adding X0 and Y0 is not even in the picture yet. Okay, fine. We'll go ahead and use the carry chip and do the calculation of the carry based on X0 and Y0. Okay. This is not the best looking circuit, but it will suffice. Okay, so now this is C. How should I label this? If I were to use a tunnel to label this wire, how would I label it? In the notation in the notes, which letter do I use? K, and would this be K0 or K1? It's K1 because it is the carry generated by the least significant bit intended for the second least significant bit. Yes?
It's not possible that
Well, K0 by definition is 0, so we can skip that one.
Okay.
Yeah. Well, at least at this point, it is defined to be 0. So we go ahead and we will use another label or another tunnel to say that this is K1, because this way we can map components of this design back to the terminology that we have already used in class. Great. Now that we have, this component and this component here, I know both of these are needed in order to calculate the sum, but what is the relationship between these two? Does anyone remember how S1 is calculated in the notes? Yes? Yep. Okay, so that's just the R of those two. So we stick another R. That would be good. Take the output out of this. Take the output out of the other one. And that becomes S1. Is that okay so far? Well, once again, we want to check to make sure that I did not make a mistake. So now we want to say 0, 0. Okay, 0, 0 plus 0, 0 is 0, 0. Well, that's kind of nice. What about changing this to a 1? Okay. 0, 1 plus 0, 0 is 0, 1. Okay, that's good. What about 0, 1 plus 0, 1? Is 1, 0. That's good. What about 1, 0 plus 1, 0? Aha! What do you think? What do you think is 1, 0 plus 1, 0? It will be 0, 0 with a carry, but since I do not have that extra carry yet, it should just give me 0, 0. So now we are adding 1, 0 and 1, 0. The result is 0, 0. So far so good, okay? So far it seems to be working just fine. Do we have any questions at this point? No questions? This is all good so far? Okay. What about the carry to the third column? I mean, it's not even calculated here yet. So how do we deal with the carry to the next column? How do we calculate K2? Well, you look up the notes. Okay, what does the note say about K2? Well, let's go ahead and dig up the notes and find out. Okay, well, actually, I don't need to dig it up, but you guys can go ahead. There are two sources to that carry, right? So whenever you see an R, there should be a matching C somewhere. So when you look at this R here, there should be a matching C. It's not here yet. Okay, so let's go ahead and just slap a carry calculation thingy here. And I may not have left enough space to do this. That's why I have to move things around a little bit. Okay, so this C is over here to calculate, a potential carry. So we'll go ahead and I'm just looking at the design here and trying to figure out what is the best way to do it. It looks ugly, but it works. Okay. So there's a C matching this R. Hey, there's an R here. Where's the matching C? It's not here. Let's go ahead and slap it here. So once again, the top one goes to the top one. It doesn't really matter for addition, but for subtraction it does. So that's why I want to be sure that the first component of the R is the first component of the C, and vice versa for the second component. Okay, so now we have these two dangling output pins, and what should I do with these two to become K2? So I know K2 is somewhere, so let me use a tunnel and say, okay, we know K2 is somewhere, but how do we calculate K2? Look up the notes. Yep. Okay, so in order to calculate K2, so now we have an interesting situation because we have two output pins, this guy and this guy here, that are not connected, and then we have one input pin here that is not connected. So the question is, how do we calculate K2? Yes, go ahead.
K2 is going to be the carry of x1 and y1 plus the carry of 1, k1.
Okay, very good, because they both can contribute to K2. So let me say that one more time. The carry by adding x1, y1, that can be it can have a carry of a 1. Okay, let me show you exactly how that can happen. See, now we have a carry of 1 because of adding y1 and x1. But the other carry can also be generated because we have a carry from here, and then one of these two numbers is a 1. Then we have this carry being a 1. Now, they cannot both be 1s at the same time. Only up to 1 can be a 1, which means if I just do a disjunction, which is a regular OR, it will do the purpose by combining those two. So I need to go to the gates again, go specify a OR gate, turn the inputs to 2, and shrink the size a little bit, and slap it. There we go. Okay, I guess it doesn't look very good, but it will get the job done. There we go. That's our K2. So let's track down these wires. When you look at the design like this, if you switch to the finger tool, which allows you to change the values of the input pins, when you're in this mode, if you click on any wire, it will highlight the entire wire. So it's easy to see how components are connected. So you can see one side of the OR gate is connected to the output of this carry. The carry of adding y1, x1 contributes to one side of this OR. The other one connects to this carry, which is the carry of adding the result of adding x1, y1, and the carry of adding x0, y0. So this becomes K2. How do we use K2? It feeds into the next column. What do you think the next column is going to look like? I would imagine it looks something like this, minus these two. Is that making any sense? Well, let's go ahead and do this one more time, and then we'll rip this thing apart and then do it in a much more elegant way. Okay. All right. So copy and paste or duplicate. So now we're dealing with x2, y2. But for the most part, we are just duplicating the whole thing. So that means these two components will need to be duplicated. And they can look exactly the same as before. The blue wires are indicating that we have a problem because they're not connecting to anything that actually specifies a signal. So it can be fixed by just making all the right connections like that. Okay. And we can also copy this. It becomes our Q2. I didn't make this design very easy to copy and paste, so I'm just looking at spacing here, and that's one more up. There we go. Is it lining up the same as the first one? Looks like it should be here. Okay, there we go. Don't worry about the red and stuff like that. We'll fix those later. Okay, where do you think this carry goes to? It's mirroring this carry. What is that? Yep. Okay. What about this R? Where do you think that R should go? This R is basically this R. It has to go to the second input of this R here. What are we missing? What about this? What about this connection? Where does it go? Oh, it comes from the carry of the previous column. Where is that? It's our K2. Now you can wire from here, or you can just have another tunnel with a label of K2. I'm not going to do that trick just yet in this class, so we'll just go ahead and bring in the wire physically, like so. And that's our third bit. And what about the fourth bit? Copy, paste, modify, right? Has anyone told you, any professor in programming told you, every time you use copy, paste, and modify, you really should think about it and go like, is there a better way to do it? No? Yes? Okay, so I know some of you have figured that out by yourself, but has anyone told you that anytime you use copy, paste, and modify in coding, you really should be thinking, is there a better way to do this? Okay, very good. So what did I just do? Copy, paste, modify. Okay, so that means I can turn some of this stuff into subcomponents. Well, one thing I do notice is it looks like this is a pretty common subcomponent. 2 inputs, one R, 1 C, and then 2 outputs. Is that making any sense to you? Okay. There was a hand. Let me answer that question first. Yeah.
So where does the extra carry go in this?
Say that one more time.
Where does the extra carry go in this? Extra carry. The carrying over bit which doesn't get processed into sum.
The extra carry?
Yeah.
Well, it's not presented here yet. Okay, but by the time I'm done with this design, the extra carry is going to be pretty obvious. Okay. So what I'm going to do is I go to project and go add a new circuit name. I will call this HA for half adder. Okay, it's only half of an adder. So the half adder is going to have 2 input pins because it is once again adding 2 bits. So we'll label these, just using the usual terms, X and Y. It's going to have a carry function. It's going to have a result function. And these 2 outputs become the actual output here. So we'll put one here and put the other one over here. Okay. That's all I'm going to do. This is called a half adder because it is performing one single simple addition. It will give you the result, it will give you the carry, but it is not the entire column, not yet. Is that okay so far? Okay. So I'm going to turn this into its own circuit. Right click, edit circuit appearance, and we'll just call this a half adder. Label this as HA. But anytime you have something that has multiple output pins and the input pins, well, you should technically label both the output pins and the input pins, but in this case, the output pins are particularly important because I need to know which one is R and which one is C. So this would be particularly helpful to me when I use this as a component. Any questions up to this point? Okay, so we have to remember what the HA is. And HA will take the inputs. One of the output is the R function. The other output is the C function. That's basically all it does. Okay. And then we go back to the main design and go like, whoa, this is kind of ugly. Where can we utilize that component that we have just derived? Ooh, I can see here, right? That is one. I can see another one over here. I can see another one over here. Is that all I can do? What about these? That's another one. And that's another one. Okay. So, remember what I said? I'm going to rip this apart and then redo it. That's what I'm going to do here. So we'll take out all the guts of the current design. Get rid of all of this stuff. Get rid of all the extra wires. The OR gates I'm going to keep for now because they are kind of important. But instead of using all those small individual components, I'm going to slap these HA components here. Aha! Okay, so this one is pretty easy, and HA goes here. The result becomes the actual sum. The carry would go to the next one. but the other one also has a half adder here, combining x1, y1. Okay. And we know that there's another half adder here. Now, for the other half adder, it's taking the result from the first half adder as one of the components, but the other component comes from the carry. Okay, let's just pause here for a moment and make sure that we understand what this means. Okay. This wire is what? Q1. Okay, so this is Q1. I'm just going to use a letter, use a text here. This is Q1. There we go. Is that okay? What about this wire? What is it known as before? It's a K, but which K? K1. That's right. Okay, very good. So when we combine K1 and Q1, what is the result? Where should this go? What is the R? What is the result of R, Q1, K1? Sum 1, yeah. So we connect this one to the sum. There we go. What about this dangling carry? And what about this dangling carry? They go to the inputs of the OR gate. Because they will help compute K2. Right? Okay. What do you think this picture is going to look like for x2 plus y2 getting the sum S2 and generating the carry for the next column? It's going to look exactly like this. Is that making any sense? The structure would be the same. Now, how do we know that structure is almost the same, exactly the same, other than bit 0? Where in the notes, when we talked about this in the lecture, which part of the notes reminds you to go like, oh, this is going to be the same structure for all of the other columns? When we use the generalization of SI equals blah, 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 QI equals blah, 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 they all depend only on that column, or sometimes the column before that. So that's how we know that we can create a common structure to compute all of these sums. Okay. So we look at this and go like, okay, can we turn this thing into its own design? Well, as it turns out, it's pretty easy to do it. Okay, so we'll go ahead and select this, copy, and I go to project, add another circuit. This time it is a full adder, so I use FA to represent it. Paste. All right. Well, we're missing quite a few components. Not a problem. We can just go ahead and specify the input pins for these two. Oh, what about this wire here? It is supposed to be the carry from the previous column. Okay. So we need one more input in this case. Okay. What about this one here? This is an output, but it's not going to an output pin. Maybe we should change this to an output pin. There we go. So now we have a new circuit, but it is really helpful to label the pins for the new circuit. So let's go ahead and label this one. This is, I will label this one as C in for carry in. I will label this one as C out for carry out. And then these two are the same as before, they're just X and Y. And this is sum, but not S1 anymore, it is just a sum bit. So this is how we can create what we call a full adder. Yeah, go ahead. Okay. So you can see how two half adders and a OR gate will make up for a full adder. Okay, so now we take this and we say, okay, let's make this into its own component by using edit circuit appearance. So this time it is really, really important to label the pins because now we got 3 input pins and 2 output pins. So for the 3 input pins, the first one is C in. The 2 output pins, one is, this one is sum, this one is C out. And then the other 2 pins, which is this one and that one, label 1 is X, label 1 is Y, and move the labels a little bit so it looks nice. There we go. Now we have a full adder. Yep.
Let's just look at this wiring of the full adder real quick.
Sure.
Okay, thank you.
Is that okay so far? Yes? Okay. Now if you still want to keep the labels, you can keep those. Except this is not Q1 anymore, it's just Q. And that's it. I think we got everything here. And this is also K, this is the K of the next column. Alright, so now that we have this component, we go back to main and say, okay, let's rip this up again. When you're doing your programming homework assignments, how many people tend to just completely start the project over again, when you say, oh, there's a much better way to do this? Nobody? Okay. I do that all the time. When you go out to work, your boss probably won't like it. Because when you go out to work, your boss is much more concerned about the throughput. Are you getting code done, not whether you are getting code done right. I have personal experience with that sort of thing. So, yeah, it's unpleasant. All right, so now that we have full adders, let's slap some full adders on here. 1 full adder per column. So we have 1 here, 1 here. Okay, let's just kind of stick with a 3-bit adder because the 4-bit adder is going to be pretty much the same thing except it's just one more bit. Okay, so we know there's a S2, excuse me. There's a S2, which is the most significant bit of the sum. We also know there's a overall carry for the entire design, which is also going to be an output pin. So we'll just call this, overall carry or just carry out for the entire adder. Now our task is to go like, okay, how do we hook up these pins? These input pins into the components and then the output pins of the components to the actual output pins. What do you think? Just by the labels, the name of the labels, I think you kind of know how to hook up some of these pins or some of these components already. The C out, where do you think they should go to? Yeah, C out goes to C in. Yep.
So for the first full adder, does it matter that you have the input port for C in when there's no carry?
We'll fix that later. But that's a good point. That is a good observation. Because what is the C in into here? Because we don't want to leave any pins unconnected. Remember that? So we'll figure that out later. Okay? But we'll do all the really, really obvious ones first, which is C out. We go to C in. C out. We go to C in. Now the wires are red at this point because the circuit is not done yet, so it is complaining about certain things cannot be determined. It's okay. We'll fix that later. And then the X and the Y will just go into the XY bits, right? So 1 bit from X, 1 bit from Y, go in here, 1 bit from X, 1 bit from Y, like so, and the same thing here. Pretty boring. Like that, okay? What about the output dot that is labeled S? Where do you think they should go? They're the sum bits, right? So we just go connect these things to S0, S1, and S2. All right? So once again, don't worry about the red wires because at this point some of these things cannot be calculated yet because the circuit is not entirely done. What about this C out? Where do you think it should go? The overall C out, the overall carry for the entire 3-bit by 3-bit adder. Okay, so let's hook up these two. We're almost done, except for this, okay? Because of the lack of a C in, the sum cannot be calculated because we don't know what it is. What do you think? If I really want to use this particular structure, what do you think should be C in for bit 0? 0 itself, a constant 0. Very good, good job. So constants are actually under wiring. So when you go under wiring, you can go to constant, pull a constant out. You know the default constant value is 1. Just change it. Change not the data bits, but the value to 0. Okay, it wants a hexadecimal 0. Fine. Picky. Okay, so now we have a constant 0 that goes to C in. The whole circuit is done. Yep.
Can you just need to have that in the first one?
You could, but in general, you know, that's okay. This is why we have the carry out having its own bit on its own, and the processor can remember the carry out of the previous addition operation, because you can't feed this C out of one addition operation as C in to the next operation. But at this point, I'm just going to assume it's a 0. Okay, so I'm not going to stack, you know, add operations. But there will come a point of time when it is really helpful to be able to stack these things. Okay. All right, so we got the design pretty much done. It's time to test it. Now, one thing I really don't like about this particular design is I'm splitting the bits, you know, all over the place. Because y2, y1, y0 is one number. x2, x1, x1 is another number. So when you look at it, it's kind of like, wow, that's kind of really awkward to look. Because if you want to look at these as traditional numbers, you kind of have to tilt your head like this so that it looks right. Okay, so it's up to you to kind of rotate the whole thing and so that everything looks right again. But you know, I can still read this. Yeah, it's just kind of awkward. Okay. Well, let's try out several things. Give me some numbers to try. Go ahead.
Oh, I'm sorry. I had a suggestion.
Yeah.
Is it possible to have one single X?
Yes, you can. But then you will have to split the wire into multiple parts. So I don't want to complicate things, you know, even further, because this stuff is already kind of complicated. So we can optimize the design later on using a multi-bit pin. Okay, but at this point, I'm just going to leave it the way it is. Okay. So give me some examples. Okay, you don't have to think in binary. Give me any numbers, you know, so that each number is from 0 to 7. That's all I need. Give me 2 numbers. Each one is from 0 to 7.
6, 4.
6, 4. Okay, very good. 6 is 1, 1, 0. So let's switch to here. 1, 1, 0 is Y. 4 is 1, 0, 0. That is 4. Let's see whether the result is right or not. The result is a 0, 1, 0, which is a 2, but we have an overall carry. What do you think this overall carry is representing as a value? Okay, let's check it out. This is telling me how many 2 to the power of zeros, power of 2 to the power of 1, 2 to the power of 2. So the carry is telling me how many 2 to the power of 3, how many 8s, right? You know, so we have 1 8 and 1 2, which is 10. Is 10 what we know as 10 in decimal? Is that the sum of 6 plus 4? It works. Okay, another example. 5 and 9. 9 doesn't work because I need each number to be from 0 to 7.
7, 7.
7 and 7. Okay, 7 is 1, 1, 1. So we want y to be 1, 1, 1. Y is 1, 1 already. We just have to turn this one to a 1 as well. X is 1, 1, 1. So the result is 1, 1, 0, which is a 6. And then we have an overall carry. But the overall carry in this case is representing an 8. So we have 8 plus 6, which is 14, which is 7 plus 4, 7 plus 7. So the design does work. Now you would go like, oh, great, so we are done with binary addition and we can just move on. Well, if you read the notes, you will realize that we are about 2/3 through, and then there's some really ickish, math stuff after this point. You go like, how can this not be done yet, right? Now this is a really good picture to show you why it works, it is very elegant, and yet it has a serious problem. Okay? Look at all the carries. Now I'm going to highlight the carries. So carry in is not a concern, it's just an input. So you can hook up this to a constant, you can hook it up to an input pin. Either way is okay. But you can see how this line is really important. In other words, the output of, okay, I'm going to use the mouse pointer. The output of this particular full adder is meaningless until this wire has settled down, is done computing, right? But the output of this one is useless until this whole thing is done, which means I cannot look at this output and use it until this particular full adder is done. In other words, we have a problem of each full adder is depending on the carry of the previous full adder before the current full adder can do any useful calculation. They are waiting on each other. Okay? This guy is saying, oh, my output doesn't mean anything until you are done. This guy is saying, my output doesn't mean anything. There's an output, but is it the right answer? I don't know. I don't know whether my output is the right answer until you tell me what is your carry out. So when you have a 3-bit thing, it's not a big deal. Okay, you have like two components waiting on the previous one. What if you have a 32-bit adder? Then you have 31 full adders waiting for the previous one, and it's a chain, so they have to wait on each other. When you are moving on to 64-bit adders, then the amount of time it takes to add two numbers is going to be twice the amount of time for adding 32-bit numbers. Do you see the problem? It doesn't scale very well. So this is called carry rippling, because it's kind of like a ripple effect. You cast a stone into a lake, okay, the ripple goes in here, and then that ripple in return generate another ripple, and so on. Now this picture doesn't really quite convey the problem because we are only dealing with 3 bits. But when you imagine this is like 64-bit long, then you will start to see, go like, wow, that's really a lot of weight, for the answer of the previous full adder. So that's why, traditionally speaking, when people talk about adders in a class like this, they talk about this design because it is simple, it's elegant, it is easy to put together. But in terms of efficiency, it's not good. In other words, if you take this design and you become an Intel engineer and you put this into the next processor, you'll get fired. Because it is really, really slow. So what do? Well, you read the rest of that module. So instead of using carry ripple, you use carry lookahead. So the carry lookahead mechanism, which is what we will talk about next week, okay, is a mechanism where you can have almost constant time calculation, almost constant time addition calculation, regardless of how many bits we are dealing with. Wow, isn't that a vast improvement over something that is, determined determined by the width of the integers that you're dealing with? Because this one, the actual time for the calculation is based on how many bits you have in an integer. If you have twice the number of bits, it will take twice as long. But the other design is almost constant time. Regardless of the number of bits in an integer, it still takes the same amount of time to calculate. Now, circuit is a little bit more complicated, for sure. Okay, but these days, people have computer-aided design, which means a lot of stuff that you specify in a processor, they're not done by hand. They're generated by a computer. So as long as you know the basic pattern of what each one should look like, you can just program. You can write a script. It can generate the proper circuit. It's not a problem. So that's what we're going to talk about next Monday is, how do you take the basic stuff. We'll keep the R function, we'll keep the C function, okay? But how do we change the structure of this whole thing so that it is no longer relying on the carry to ripple? Instead, it is constant time for all the bits. That will be the end of today's lecture, and I already give you a tie-in to the next section and the topic that we'll be talking about next week. So it would be a good idea to finish reading the module that we started today. Make sure you understand the notations first, okay? Because we went through some notations, we went through some pictures, some examples. So try to tie in everything, so everything is solid up to this point, and then move forward and look at carry look ahead, the mechanism and the math behind it. Okay. All right, so I'm going to stop the streaming and the recording. If you guys have any questions about the lecture material or the lab material, I'm here to answer those questions.